Yeah. So essentially here what we did was we have the number of positions, there's five. Goal position, it set it to -1, but you can also just set it to 4. Start position 0, actions left or right, and then you can define what left and right mean later. And then for positions, we just made a list of the range of num positions. So range, remember, will create you an array that goes from 0 to the whatever number you pick -1. And so this will give you a list from 0 to 4. And yeah, it'll have goal position equals to 4. All right. Now, you guys know what a state is. So the state is the current position on the line. So currently the position of our agent is at 0, and we want to have it reach 4. So now we need to define actions. How are we going to take these two actions that we have? We have this list of left and right, and we need to create a function that takes the current state and an action that the model chooses, left or right, and then return the new state. So find a way to translate the model taking this left or right, so like indexing one of these positions and actions, and then having it return the new position after that. Your questions, let me know. Do one quick hint. The function that you're gonna have to define needs to take in a state and an action. Sometimes just having the parameters that you're going to be providing helpful can be very useful. Give you another hint. Here you have you need to return the new state and the reward. So you have new state equals, currently it's just the original state. And then the reward is 0. And then once you take your action, it will update these two. Give you the main stuff for action as well. Then you take the right action, then your new state is either your old state +1, or it's the goal position. The minimum of that is goal position at the end. And then if your action's left, then it'll be -1 in start position. This way, it just prevents you from, when you actually try to figure out your new state, it'll prevent it from going out of bounds. Error. Does everyone get like this logic here? Why right and left are this +1, -1 and the minimum? Let me know if you guys get this done, so then I'll just move on. Or I'll add in another hint. Yes. Good. This is the final stuff. So new state is equal to the goal position. So if it's in the right place, then you'll add some reward and you're going to return then the new state and the reward. So if your new state isn't in the right place, then you want to basically give a reward of 0. If it is, then it's a reward of 1. Typically, what I would have done in this scenario actually would have been more so, and they might just do this later, but I would have made it so if you're getting closer to the state, then you have a reward. And then if you get at the state, then you have like some really big reward. So because that way it actually trains the model to go towards the state rather than just try to randomly go left and right. But we can see here that in the like parameters of like what we're supposed to be doing, we can only get a reward when we reach the goal state. Otherwise, the reward is 0. So someone tell me, what do you think the behavior of this is going to be? If we just do this take action thing, we run it with the reinforcement learning agent over like a bunch of times, what's the result going to be?
Either 1 or 0.
I mean, yeah, that's after the first one. But I mean, like, if you just run this like 1,000 times for the same agent, what do you think will happen? Will it go towards the final point? Or will it just start jumping around randomly?
Jump it.
Yeah, it will. Because it doesn't have any notion, given how much reward it's getting returned, of what actually is closer to the end goal. Remember, it only gets reward when it's at the goal state. Otherwise, the reward is 0. So it doesn't know whether it's actually getting closer or farther. So it's going to keep jumping around randomly until it somehow ends up at the final place. So then we can do the task 3. So take a single action. So you simulate an agent that's starting at the position 0 and have it take the action right and then print the starting position, the action, the new position, and the reward. This one should be a little bit simpler because we already defined take action up here. So I'll move past this one in a couple minutes. Giving 1 more minute on this one, and then I'm gonna move on. Should be pretty simple. Here we have what we're going to be doing. We have current state equals start position. You actually don't have to do this first step either. You can just supply start position directly. But this is useful because in case you want to do anything else with the state without having to alter start position, because in later steps you're going to have to change the current state. So we're starting at current state. This will return 0. Our action is equal to right. Or in this case, you can also do we define this up here, so you can also do actions of 1. So you can also take actions of 0, or no, sorry, 1, left and right. And so then it'll return out the new state and the reward based off of that, because remember, we returned those 2 from this function. And then you can print those 2 out. Pretty simple. All right, so now what is a reward? Yeah. So the reward is the feedback. And in our tutorial world, remember, we get 1 plus 1 if we reach the position, otherwise we get 0. So let's try making our way to the goal. Reset the agent's position to the start. Remember, we have current state is equal to 0, so that's fine. We can just start at current state. And then simulate the agent taking right for multiple steps. So up to 5 steps, because otherwise we'll go out of bounds. So just make it keep going right. And then for each step, print the new position and the reward earned. And then you sum up the total reward over these steps and then display it at the end to show when the goal was reached. So try that out. And hint here, I'd recommend using a for loop to try to iterate over because we need to do multiple steps. So what you can do is you can do for I in range 5, and then you can just continue doing like that. And then you can put the take step function in between. And then remember, you also have to update the current state. Otherwise, you're gonna end up in an infinite loop where you're just gonna keep creating this new state, but then your current state reverts back to 0. So remember, at the end of your for loop, that you have to update your current state so that it actually moves rather than just like taking a step and going backwards. To do this, we need to define total reward and state. I'll give 2 minutes on this. Keep going, keep going. I recommend using a for loop here. You can do while I is less than 5 and then like keep adding, or you can just do 4, 5, and 5. Now you don't have to worry about like any problems with infinite loops. Because then what happens is if you forget to put the I plus plus, then you'll end up doing it infinitely. Okay. All of it. Pull that. Yeah, great. I'm just looking that you updated the state. And here's the second part. Remember, if we do reach the goal position, then we want to cut that. We want to stop the loop right there, just in case the goal position comes early. Then this break function will break the for loop. Yeah. Again, we have here actions equals rights, but we can also change that. Remember, we want to take action. Yeah, I'll just give you the rest. Like that. Here we can see we have one step, we have our action. We're going to be taking that action, and then we're going to be updating our state. So we're going to make basically our state +1, and we're going to update our reward as well. So remember, this will return a reward. If it's 0, it won't do anything. If it's 1, then we found it. And then after it's done with the range of number positions, we'll do episode complete. And this total rewards should end up being 1. All right, now this is kind of similar to the last one. You basically want to make a simple decision-making loop where the agent keeps moving right until it reaches the goal. So at each step, record the action taken, the new state, and the reward. Actually, I think that's just this one. Yeah.
It's just like it doesn't hit the goal like multiple times. It only hits the goal once instead of second one. Like it won't be at the goal for multiple steps.
Oh yeah. This is the same thing as earlier. Actually. Yeah. So that's your first reinforcement learning agent. Keep in mind, this is very simplified. So in the real world, the state is more complex. There might be more actions you can take. And this one also is very algebraically solvable. So like this one, it's pretty easy to reach goal position if you just find your goal position and then like subtract your current from your goal, just add however many steps that is. In the real world, you might not know, even like a human might not be able to estimate what exactly to do. And the environment is usually a lot more noisy and less predictable. So it'll be more difficult to actually, like the policy will be more difficult to estimate what action is best. And then also, the policy is not hard coded. Like here, we said always move right. Typically, your policy is going to end up being some kind of model. It's going to be like a mapping of state through action, and it's going to learn that through trial and error. So, like same way how you train like any other model, you can also train a reinforcement learning model based off of how much reward it ends up getting. Um, and you train it to maximize that reward, and it will learn its policy along the way. So, and typically also you can use neural networks as policy. So you can take a neural network, have it input the state, and then have it output a action. And so you can use that to then try to justify your reward. And that's really useful because let's say that your state is like an image. Let's say you're making like a drawing model that wants to like draw like a human. So you can have your state be an image. What is your current image? What's your current picture that you're drawing? And then it'll take out an action like, okay, let's add some lines here. Let's add some color here. Let's add some shading here, things like that. So that would be really useful if you had a convolutional neural network as your policy. And then, yeah, the agent learns from rewards. Here, because we have one policy only, move right, this didn't really come up. But typically, your agent would try multiple things out, observe the reward, and then adjust its behavior to maximize the future rewards. So one way that it could do this, for example, is if you had, if you train this over multiple times, at the start, it would be very random. It wouldn't really know where to go. But if you had it, for example, like if it's getting closer, it'll increase reward. If it's getting farther, it'll decrease reward. Then your model will know that, okay, if I go in one direction and it's increasing my reward, I should keep going in that direction. And so it'll learn kind of like a human learns. And then here, our environment's deterministic. So like an action always has the same effect. But in the real world, results can be uncertain. They can be slightly random. So for example, one type of this is like chess. So in chess, moving a pawn does not always have the same effect depending on the situation of the game. So like moving a pawn in one situation might have a really high reward, while moving a pawn in another situation will have a very low reward. And then even still, that's like still effect in terms of reward. There's also just effect in general, like how it'll actually do. So like moving, like an arm, for example, a robotic arm, moving an arm from 0 to 15 degrees is like one kind of action, but then moving it from 15 to 90 degrees is another action that does something different. And so here, even though the action is still going up, it has a different effect. So, but this is still essentially building intuition about how when you have an agent and interacts with this environment. So we had this environment, which was like a list of numbers. We had an agent that just takes steps, and we got there. Yeah, that's the lab. Do you have any questions? Cool. Great.